Here we have the function x squared plus 3x plus 2 dividing by x plus 2, and we want to show that this function is discontinuous at x equal to negative 2. So first let's look at the definition of continuity at a point. The definition says that we have a function f of x, it is continuous at a point at a if we can show the following things. If f of a is defined and the limit as x approaches a exists, and the limit of f of x as x approaches a is the same as f of a. And for this example here, we want to show that f of x is discontinuous at x equal to negative 2. And so what we need to show is that it doesn't meet one of these conditions is not met. And that's how we show that the function is discontinuous at negative 2. And let's look at the graph of the function first. And so at negative 2, here's the graph, and then we have a hole at negative 2. So graph, the graph of this function right here has a hole at x equal to negative 2. And now let's show that this function is what we mean by discontinuous at x equal to negative 2. And so first, let's find f of a. In this case, a is referring to the negative 2. And so we say, well, let's find f of negative 2. And so in the place of x, we just put negative 2. And we end up with 0 over 0, which is undefined. And therefore, f of x, the function, is not defined at x equal to negative 2. And so the first condition here is, does not fails. And in order for a function to be continuous at a, or in this case a is negative 2, all three conditions we have to meet all three conditions. And already the first condition fails. And therefore we say that f of x is discontinuous at x equal to negative 2. And whenever we have a discontinuity where we have a hole like this, we say that f of x has a removable discontinuity at x equal to negative 2. And in a few minutes, we'll look at examples where x has something called non-removable discontinuity. Here we have the function of absolute value of x dividing by x. And if we graph it on the graphing calculator, this is what it looks like. So we have an open circle here at the point 0, 1, and then we also have an open circle here at the point 0 and -1. And then also the definition of absolute value of x is equal to x if x is greater than 0, and it's equal to -x if x is if x is less than 0. And again, to show that the function is discontinuous at x equal to 0, then we need to show that one of these three conditions fails. And so we can see right away that if we do f of 0, then we get 0 over 0, which is equal to 0 over 0, which is undefined. And so condition number 1 fails. Okay, condition number 1 says that f of 0 must be defined. Defined means it has to equal to a real number, but in this case it's not equal to a real number. In this case it's undefined. So we say that f of x is not defined at x equal to 0. And therefore, this function right here is discontinuous at x equal to 0. And then at x equal to 0, we have a gap right here. Whenever we have a gap like this, we say that x has a non-removable. So this function right here has a non-removable discontinuity at x equal to 0. And then other than that, the function should be continuous everywhere else. Okay, if we look in the graph, we don't see any gap, any holes, or anywhere else. And so in this case, if the function is continuous and normally we write it like this, from negative infinity to 0 and then union 0 to infinity. So it's saying that f of x is continuous everywhere except at x equal to 0.